Okay, let's see if I can make this work today. Um, we're on. I'm almost through grading the first homework. I've got one problem left to look at, and so I'll be done by this afternoon. So as soon as those grades go into Blackboard, if you notice that, then if you're eager, you can come by and pick up your homework at my office before Wednesday. But in grading those, one thing, so a couple things occur to me to comment on in general. Make sure that, for instance, on the sample test, if this thing will open, yeah, there it goes. So I know this is, I know you're learning how to do this, so it's not always easy, and it sometimes slows you down in actually answering the question. Okay, because again, the answer to the question may occur to you before you carry out this step, but this step is really important to your long-term ability to solve problems like these. So that's why I'm stressing it. So if it says, if it gives you some counting problem, right, describing some set, and a lot of the problems in here are going to be counting problems, almost all of them, in fact, right? Then, and if it's so, in the sample test, it says write a model for that set. So try to do that, right? Okay. Try to write down either a set model that corresponds to the set that you're interested in counting. So we practiced that a little bit, right? Okay. If you look at the solutions to homework number 1 that are posted, a little bit of that is in there, okay? But that homework was less focused on this particular skill than, for instance, the second homework is, right? But anyway, if that's there, then you really have to try that, okay? I mean, you really have to work on that. Or, alternatively, right, our second counting technique is to describe an algorithm, right, for generating an element in the set that you're interested in counting, correct, right? And then trying to figure out how to count the executions of the algorithm, right, to count the set, right? So we have these two, and these two techniques are complementary to one another, okay? So when you do both of them, you'll actually see they're quite similar to each other, and sometimes we use a mixture of the two on the same problem, okay? So we'll have both a model, a set model, and an algorithm in the same problem to count a set if it's a particularly complicated problem. Now, some of the questions a little bit later on don't specifically ask for this. They're just straightforward counting questions, okay? But again, really, when you're actually counting a set like this one, you really are going to be doing one of those two operations. You're either going to be mentally building a model, or perhaps explicitly building a model, a set model for the set, or you're going to be mentally thinking of how do I construct an element in this set? What is a procedure? What's an algorithm for constructing an element of this set, right? And then once you've described that algorithm, then you can count the number of ways that algorithm can execute, right? So you're going to be carrying out this process implicitly, even if you're not doing it explicitly on later problems, okay? But on the problems that it asks you, I think Kaylee is already thinking about how to solve the problem, okay? On the problem where it asks you explicitly to do this, or on the parts where it asks you to explicitly to do this, again, pay attention to those parts. Try to write that down. Think about that, okay? All right. Even if you're like thinking, well, the answer here is obvious. It's got to be 128, right? Okay. You've got to back up and try to follow my instructions, okay? Even if it seems a little bit nitpicky. All right. Okay. So there's a caution on the sample test. That came up a little bit in homework number 1, where, particularly on that dice problem, where you were coloring faces of a dice. It said write down a set model, and some people were answering the question but not writing down the set model. And I know we didn't have much practice with writing down set models at that time. Okay, so that was hard to do. But anyway, you have a little bit more practice now, especially after we get through going through all these notes. Okay. A lot of you poured some really beautiful logic into some of these problems. So for that, I really thank you and congratulate you. That was sometimes logic was really nice, particularly on that problem 2, where you're deleting a square, right? Okay. So I didn't grade that problem explicitly, but I was reading solutions from that people turned in, and some of y'all thought really hard about that particular problem. And also, I know you thought hard on the dice coloring problem as well, even if you didn't write down the model very clearly. I know you thought about how to answer the questions, except for the last one. Okay, the last one was where you didn't have the faces of the die numbered, and you were just coloring red and blue. That one that one was much more difficult because it's much harder to think of a set model for that particular problem. And see, when you cannot think of a set model or an algorithm for counting, it makes it hard. That was much harder for you. Okay, so this is why the set models and the algorithms are so useful for us. Okay, if we don't have those at our fingertips, we're really stuck with sort of just enumerating all the possibilities, and that's not always easy to do. Okay, you have to think about it very carefully and systematically. So a lot of y'all missed that one. Okay, but the solutions to the remember, the solutions to the homework number 1 are posted. So there's my second recommendation. Make sure that you read the solutions, right, to homework 1. Read through those. They're quite detailed, so because I was trying to put enough detail that you could understand the solutions, but so you may not want to read all of that detail, but try to read it enough, right, that you grasp the sort of, right, the fundamental method that was used to solve the problem, right? Okay, you can understand sort of the idea, right, that was used to solve the problem. Okay, particularly on those really sort of challenging ones, like how to color that third dice coloring problem, right, where the faces of the dice are not numbered. Okay, so those are just sort of comments. Now, so we're going to put the test off. I mentioned that last week. So let's aim for next Wednesday, because I want to get through as much notes as I can on set models. So I've got the notes to finish chapter 2, and which is all about set models. And so I'm hoping we can get through that. But we'll have to see how. I don't think we're going to get through all of that with sufficient time for the test. But we'll see how much of that we can get through. And some of these, and this sample test incorporates problems from all types of problems from chapter 2, except I don't think there's any probability problems on here. But the probability problems are kind of straightforward once you've got the chapter 2 talks a little bit about probability, because a lot of combinatorics was developed for the purposes of probability, finite probability, and but I don't think I have any finite probability problems on here. But once you've got the counting techniques down, the probability questions are very easy. Okay, this level of probability questions are very easy. Finite probability. Infinite probability is a much harder thing. All right. Okay. So let's aim for next Wednesday for the test. All right. Instead of this Wednesday. So that gives you a little bit of time. Now, I did, however, just to keep the pressure on you, right? Just to make things continually excruciating. I did post homework 4. Okay, so this is other problems from chapter 2. So these are all counting problems. So almost always the answer is, a number, 723 or something. That would be a unusual answer. But some sort of a number is the answer to these. Okay, and so it's just a matter of, again, finding a model. Okay, even if you don't write it down explicitly, this is what you're going to be doing mentally. Finding a set model to model the set, or it could be set models sometimes to model the set, or finding an algorithm to create elements in the set, or a combination of the two. Okay, that's what will be going on subconsciously when you answer these questions. There's a homework 1 solutions. Oh, what about homework 2? So so are y'all ready to turn in homework 2? You want to turn that in today? Because I will post the answers immediately. Because I've got the answers written, so I can post the answers to homework 2. And then again, you should read the answers there. Okay, so these are. I can't remember what's in homework 2. Oh, this is this is still from chapter 1, right? Okay, so there's poison cookie and yeah, so right, that's right. Yeah, so there's not really a lot of counting really in this homework, right? It's more.
There's only a 1 set model problem, I think.
Yeah, and it's a lot of and this is a lot of logic too, right? But some of this was more algorithmic. I think you were asked to, use de la Luber's method to build a magic square, or write down a Latin square, right? Okay, or things like that. The ones I remember being challenging are why are there only 8 magic squares of order 3? Okay, so that takes a little bit of work. And then the last problem I remember it was a tiling problem. If you had a Christmas tree chessboard. A chessboard where the top diagonal is cut off. Why does it not have a perfect tiling, right? Okay, a perfect cover. That required a little bit of logic too. All right. Well, anyway, so I will post those then immediately, and you can start looking at those. All right. Okay. Finally, I think I have all the procedural stuff out of the way there. Yay! So let's get to the fun stuff, which are the notes. So these problems now are all counting problems, and so in all of them, again, of course, we want to come up with the answer, but we also really thinking about what sort of algorithm we can put behind the problem to build an answer, or what sort of set model we can put behind the problem to answer it. Okay. All right. So. So we stated last time that basic theorem, which helps you enumerate the executions of an algorithm, right? Okay, and that had to do with if you had a sequence of branch points, right, in the algorithm, and you knew how many passive execution there were following each branch point, then you could count the number of total executions for the algorithm just by multiplying the number of executions at each branch point, right? But this has to be a sequence of branch points, right? Okay, branch points that are decisions that are taken in sequence. All right, so let's just apply that idea to some very simple problems, and you probably know the answer to these problems already, because these are pretty straightforward counting problems. All right, so and you guys I know have some practice with counting sets prior to this course. So passwords for a particular system consist of just 10 lowercase letters or digits, right? Without a repeated symbol, how many passwords are possible? Okay, so that's a really very standard counting problem, right? And but I want to point out that we really don't have a really good set model for this particular to answer this particular question yet. Okay, but and we're going to address that issue a little bit later here. Okay, but at the moment there's really no set model that quite captures this particular situation. All right, so because you're not allowed a repeated symbol, right? So you can't have a repeated symbol in this problem. What do you want to call this? What do you want to call this set here that we're working with? P for passwords. All right. So let's P be the set of passwords. All right. Now look. Suppose that just for a moment here we take off this restriction. Okay. So suppose that we eliminate that restriction that you cannot have a repeated symbol. All right. That makes the problem, from our perspective, at least for the time being, that makes the problem much easier, okay, because we can write down a set model for this particular set, in this case, really easy, all right? And the reason is Look, let's see. These passwords are formed from what set? It would be what? The set of lowercase letters, right? Combined with the set of digits, right? Okay, so let's call that set L for letters or something, right? Okay, and so so we'll let L just be the lowercase letters and digits. All right. So how big is that set?
36.
Exactly right. Yeah. So that's 26 plus 10, right? So we know our alphabet. That's 26. Okay. And then there are 10 digits, right? 0 through 9. That's 10 digits altogether, right? So the size of that set is 36. So Dalton, we really don't care about really the symbols in the set L that much. Okay. We're going to care if we were programming this and checking these passwords, right? But for our purposes of counting, right, we really don't care about what particular symbols are in that set. So we can actually make a model for this set L, right? Okay, that suits our purposes a little bit better. What would be just an easy model for the set L, not the set P yet, right? Okay. Yeah, just an intersect segment, right? Okay. So so you might as well think of L, right, as just being this integer segment. Let's see, what would the cardinality of that integer segment be? Obviously, what? 36, right? Okay, and so there's clearly a one-to-one or we can clearly set up, right, a one-to-one correspondence between these two sets, correct? Right? Okay, just by literally, right, saying, oh, I'll let letter A be 1, I'll let letter B be 2, I guess letter Z would be 26 then digit 0 would be 27, digit 1 would be 28, and so forth, right? Okay, so very easy, right, to manually set up a one-to-one correspondence between these two sets. So since we can work with this set maybe a little bit easier, right, than the set L, then let's switch here to using this integer segment instead of L explicitly, right? So now, once you've got this model, though, for this set L, right, then it's easy now to build a model for P, correct? Okay, because well, what's P going to look like? It's going to look like a tuple. That's right. Yeah, it's going to look like a tuple. Correct. Okay. Of course, you're not going to have the commas and the parentheses, right? But the words in the passwords in P, right, are essentially going to look like just a tuple. And we know of how many of them? 10, right? So those things in P are essentially going to be the same as a tuple. So we have a very easy model, right, for P. That can just be what? How do we generate tuples? What operation does that for us? What?
L cross L.
That's right. Okay. So, but in our case, what? Yeah, this integer segment, right? Okay. So we can just use this integer segment, right? Okay, and cross it with itself. Yeah, we'll use it as a factor 10 times, right? Okay. So use it as a factor 10 times. So we might as well write that as 36 to the 10th power, although that's not really quite correct, right? But essentially, right, this cross product where 36, this integer segment 36, right, appears as a factor 10 times, right? Okay, so that's kind of an obvious model, right, for P, right? Just pick out a tuple in there, right? That's going to be a tuple of where each coordinate, right, is a number from 1 to 36, and then you produce a password from that, right, just by looking at that number, and then figuring out, right, what letter, right, or digit, right, that number corresponds to, and that's how you create the password, right? Does that make sense, Taylor? Yeah, so it's kind of obvious, right, how tuples in this set, right, correspond to passwords, correct, right? Or vice versa, how you can take a password, right, and turn it into a tuple in this set, okay? But we know the size of this set, right, Taylor, because that's one of our basic theorems, right? The size of this set is what? So if you have a cross product of a set of size 36, right, where you're crossing this with itself 10 times, then what's the cardinality of that? What's the cardinality of cross products? What? 36 what? No, you do 36 and raise it to what power here? 10, right? Yeah, okay. So it's 36 to the, yeah, you don't have to tell me what 36 to the 10th power is. I don't know. Okay. So it's 36 to the 10th power, right? Yeah. So there's the cardinality of the set. But that's a relaxed version, right, of the actual problem. Because in our problem, we didn't want repeated symbols. So this is no longer a correct model, right? Okay. That's no longer a correct model because there are lots of tuples in here, right, where we have repeated symbols. In fact, here, I guess sort of the quote-unquote first tuple in this set, right, would be 1, 1, 1, 1, 1, 1, 1, etc., right, 10 times. That corresponds to the password A, but not allowed to use that, right, okay, because that's not secure for some reason. That has a repeated symbol, right, okay. So this is way too large, right, okay, way too big, right. All right, so now we have to resort to either some other sort of set model, right, or what's our other option?
Adjusting the set model?
Yeah, adjusting the set model. Well, adjusting the set model, right, okay, right, so that's some other set model, okay, or what's our other counting option, perhaps? Thinking of an algorithm, right, okay, for actually creating a password, right? Okay. Now, if we wanted to adjust the set model, which I'm not going to do here, but if we wanted to adjust the set model, any ideas of how we could maybe adjust it?
Well, since you're not repeating the letter, the cross product instead of 36, your second coordinate would have 35 options.
Yeah. So I think but that's a set model that. All right. So I see. So you're going to come up with a little bit more complicated set model here, right? Okay. So you would think of, I'm going to replace this by, in my model for P, I'm going to replace this by what? 35, right, okay. But now what does that 35 represent?
It means it can't have the same coordinate that was the last one. Whatever number the first one has, you subtract it from the set, and then that's the new set that you're cross.
Do you see what my issue is? I don't understand if let's see. So you're saying cut this down to 35, right? So this last one would be, is this 1 at the end here? No, I'm sorry. That's 27? Okay, right. Yeah. Did I use up 10 of them? I think so. Yeah. Okay. All right. But so all right. So he's saying, okay, put a 35 here and a 27 here. So let's pick a tuple out of that set. So I'm going to pick a tuple out of this set, and so I pick this one because that's still in there, right?
Well, I said the number we
so
first one.
Well, how does that tuple? How do I match that tuple with a password without a repeated symbol? That still looks like all A's to me.
Yeah, I mean, that's the way you would count it, though. That's the way you would count the set P.
Okay.
Yeah. Just like.
All right.
Okay.
Wait. Let's. All right. I'm going to stop you there. All right. I think we're going to get to your technique. Okay. But this idea, by the way, will work. Okay. So you can create a set model this way, but you have to be now very clever about how you describe this set. Okay. Right. Because that set still has 1 in it. So this tuple is still in this cross product. But now you have to describe to me what that tuple represents. It can't be all A's because it's got to be a word without a repeated symbol in it, right? Okay, so you would have to come up with some method of telling me, again, what password without repeated symbols that tuple matches, right? Okay, it can be done, but it takes a lot of words to do it. Okay. All right. So I'm gonna kind of let's not go down that road then. All right. But I had a different idea. Another set model you could come up with is, don't forget about complements, right? Okay. So we want words without a repeated symbol, correct? So that would be the complement of words that what? That have a repeated symbol, right? So you might think of, is it possible for me to count words that have a repeated symbol, right? Words that have a repeated symbol, and then take those out of this big set, right? Okay. So again, we're not gonna follow that approach, but I'm just pointing that out. That's an option for you, right? Okay. That might work, all right? Because you might be able indeed to count words with a repeated symbol with a little bit of effort, okay? And then just subtract those from all words, right? And that would give you words without a repeated symbol, okay? So don't know how easy or hard that would be, but that's another set model way, all right? But all right, so let's now switch to the algorithmic way, okay? So so can you describe an algorithm then for me that I can use to build a password, right? But it's not going to have a repeated symbol, okay? Right? So let's put that restriction back in, okay? I'm not going to change here the name of P now, okay? All right, but so that's still the set of passwords. But now I'm putting this restriction back in here. No repeated symbol. Maybe I shouldn't draw it like that. All right, so who wants to describe an algorithm for me there for creating such a password? It's kind of obvious, isn't it? Just think about what you would be doing here, right? Just think about what you would be doing if you were trying to you were sitting at the machine, right, and you were trying to create an account on this network or whatever it is, this website, right? And they want you to give them a 10 symbol password, but the restriction is you can't have repeated symbols, right? So what would you do?
You'd have 36 choices for the first one.
Well, what are you doing first there?
Picking.
Yeah, you're picking the first thing, right? Okay, that's normally what you would do in your typing. I don't think you work backwards there, right? So you would probably say, okay, I'm going to pick, first letter of my name. That's my first symbol, right? Okay, and then you would go on and do what?
Pick a second character.
Yeah, then you would pick the second one, and then you would pick the third one, right? Okay, all the way down to the 10th one. And you're very smart, so you would know, right, that when I get to the second character, I cannot do what?
Cannot reuse the first one.
Yeah, when I get to the third one, I cannot reuse what? The first two, right, okay, yeah, right, etc., correct, right, okay, so, see, you're making a series of choices here, right, they are in sequence, right, because first you pick the first letter, then you pick the second letter, then you pick the third letter, right, okay, you're not simultaneously picking all 10 letters, right, in this algorithm, right, so you're making a series of choices in sequence, and how many choices do you have at each branch point there? Well, let's count. For the first one, you have what? 36, right. And this is really important now, no matter what first symbol you choose, how many choices do you have when you choose the second letter? 35, right. It does not depend on what happened the first time, right? Okay, it's always 35, right? And then at the third one, you have how many? 34, right, okay. All the way down to the last one. Well, we were arguing this, but how many choices there? 27, right, okay. So there is your algorithm, right? It's pretty obvious that that's going to build a correct password, right? Moreover, if I told you a password without a repeated symbol, you can certainly tell me what choices were made each time, right? Okay, so I think this algorithm is going to generate passwords and only passwords. It's not going to give you something that's not in this set, correct? Right? Okay, so that's it, right? It's the executions. Each execution of the algorithm produces a valid password. All the valid passwords, I think, are produced this way. So if we can just count the number of executions of the algorithm, we know how many passwords we can possibly get. But we know how to count the executions of the algorithm because we know how many choices we have at each branch point, right, in that algorithm. So your answer is correct, Dalton, right? Okay, it's what? So it's not this, right, anymore, right? It's what?
Easy way to say it would be 36 factorial minus over.
Yeah, we're going to get to that, right? Okay. So, but for the time being, what's here at the end? 28 and 27?
Yep.
There we go, right? Okay. So there is our cardinality, right, for the set P, right? Okay. So there the algorithm really came in handy because a set model in this case is kind of messy. We could eventually come up with one, but it's kind of dirty. But here, right, algorithmically, so easy to just generate that answer. Now, again, I know already from the answers that you're giving me in class and from the little bit of homework I've seen, right, that this is the usual way you're going to count sets, okay? So this is your standard method, right? But this is not going to do everything you need, so let me warn you about that, okay? All right? You cannot do without set models. Sometimes you have to have set models, okay? All right? And often, just for convenience, we will mix up algorithms with set models. Okay? Yeah.
So if you were looking at it from a more programming-ish standpoint, would you say that the algorithm itself is like a function, and then you're iterating it 10 times, like with a loop or something?
Yeah, well, this is a programming question, right, of how you're going to implement the algorithm. So, and that's likely the way you would implement the algorithm, right, okay, is by repeatedly making the same choice, right? So you would be in a loop, correct? But what's going to change each time in the loop?
You're going to have to subtract off.
Yeah, it's the set from which you're making the choice, correct, right? Okay, so you would have some array there, right, of symbols, and each time you execute the loop, right, you would eliminate something from your array as a possible choice, right? Okay, right, okay. Or if you're really going to be, a very like a beginning programmer, right, and really do this stupidly, you would just program a sequence of if then else's, right? That's really hard to do though, because you're changing the because each time you have to change. Well, I guess you could do it, right? Okay, just remember to subtract each time, right? Your the choice you make, right, from your set of possibilities. Okay. All right. So is everyone clear on that, right? All right. Now, but we really could have managed here with the set model. Here we can also. All right. So with a set model, but that's not the easy way to think of this. Okay. The algorithmic approach really works faster here. All right. So how many passwords are possible if symbols can be repeated, but not adjacent. All right. So we put this other so now we have a new security measure, right? We're thinking about our customer experience here, right? And we're thinking, wow, it's really hard to make him think of 10 different symbols. So I'll just say you can't put a similar symbol adjacent, and then it's easier for the user to create a password, right? Okay. So they're more likely to create an account on my site. That seems to be the gold standard, right? You want everybody to create an account for some reason, because then you can start, pestering them with spam, right? Anyway, okay. So, y'all want to try that one? All right. So really quickly there. So think of it as an algorithm, right? Okay. How would you create a password, right? And then how many in sequence, just like we did in the first problem. And then how many choices do you have at each branch point there, right? At each decision point in the algorithm. But let me caution you: you must, again, the number of choices at a particular branch point cannot depend on, cannot vary. All right. It cannot. It's always got to be the same, no matter what choices were made earlier. So we're going to see an example where that's not always the case, and so you have to be careful of that, all right? Otherwise, you won't be counting the executions of the algorithm properly, all right? Okay, take a minute. That's all we've got. You already wrote it down? You don't have to compute it. You don't have to calculate it. It's going to be a large number, so which is what we want, I guess, right, for systems with passwords, right? I'm not in the. I notice I'm not in the. I'm not really in the notes describing the algorithm. It takes so hard to write. It takes so long to write that out. So I hope you can reconstruct that in if you're looking at the notes later, exactly how we wrote down the algorithm. Guess you can refer to the videotape if you're desperate. Okay. Somebody want to volunteer their solution to this, right? Okay. All right, Sean.
Would it be 35 to the ninth times 36?
Say that again now.
35 to the ninth times 36?
I don't know. So describe your algorithm for me.
So for the first letter, we can pick any of the 36 characters.
Right, yeah.
And then for the second letter, we can pick any 35 characters that wasn't the first one.
Yeah, because you not pick the first one right, okay?
The third
So
one,
I'm down with you to there. And then on the third one, what?
we can't pick what we have for the second one, but we can pick what we have for the first one.
Oh, there you go. Right, okay, yeah.
And then this continues all the way down.
Oh, I see. Right. Okay. So after, and it doesn't matter which specific letter you chose at any point there, right? Okay. That doesn't alter the number of possible choices each time, right? Yeah. Okay. So if you write that out, right? I mean the computation out. It's what? So you 36 for the first one, right?
Yeah.
Okay, and then 35 when you choose the second letter. Right, and then 35 when you choose the third letter, right? Okay, because here you obviously cannot pick this letter, right? But here you cannot pick this letter, but this letter becomes eligible again, right? So you're back up to 35, and then that pattern is just going to continue, right? Down to the choice of the last letter. So altogether, this is, what did you say, 36 times 35 to the ninth power. Right, good, perfect, right. Yeah, that's exactly a great way to think about it. See how nice there the algorithmic approach is then in that case, okay? So it would be hard to describe a set model. You could do it, okay? But much easier, right, to think about an algorithm and, again, the executions of the algorithm, right, okay? So there you have it. Just that easy. All right, now I forgot this one, okay? So, all right, let's see. So how many odd integers do we have between 1,000 and 999, right, that have distinct digits, okay? That have distinct digits. So that sounds kind of like the... that sounds kind of like the password problem, right? Okay. Because you're not here, right? We don't want to repeat digits, correct? Okay. By the way, of course, these two numbers are not. They're between, I guess, 1,000 and 9,999, right? But they're not going to count because they don't have distinct digits, right? So neither one of those are going to be in our set, right? Okay. What do you want to call that set? Just S here in this case. Misspelled integer there. So you've got these further restrictions there, right, that are put on. So let's try simplifying the problem just a little bit there, okay? And then so by just taking off restrictions. So I'm really not sure that I'm making it simpler by taking off the restrictions. But what if we just take off the odd integer restriction? okay? So that seems like that's going to make it maybe a little bit easier to count, right? Okay. So you just take off the odd integer restriction, right? And then you're just asking for there for distinct digits, right? Okay. So first, the fact that this number is between 1,000 and 9,999, right? That helps a little bit, correct? Okay, because we know we're going to have how many digits in the number. Got to be 4, right? Okay, because a 1-digit or a 2-digit or a 3-digit number is not going to be between those two values, right? Okay, so that's nice. Okay. All right, so really, in thinking of creating such a number, all we're doing is thinking of picking what? Yeah, just picking 4 digits, right? Okay, and we just don't want to do what? Yeah, we just don't want to repeat a digit, right? Okay, just don't want to repeat a digit, correct? Okay, so that sounds almost exactly like the the password problem, correct? Right? Okay, so let's think about it that way, right? So in building up, right, in just creating one of these 4-digit numbers, right? Okay, you could just select the digits, I think, from left to right, and so how many choices would you have for the first digit? 9. All right, so we have a debate there between 9 and 10. Okay. That you cannot have 0 in the first digit, right? Okay, so see, there is a little bit of a restriction there, right? Because it's got to be bigger than 1,000, right? Okay, so in the first digit there you have 9 choices, right? Then how many do you have for the second digit? 9 again, right? Okay, so there you're back to 9. So why 9? 0 becomes eligible, that's right, okay? But what is not eligible? The previous number, right, okay? So you get to add one back, but you have to take one out, right? So you're back down to 9, correct, right, okay? Now for the third digit, what do you have? 8, right, okay? So, because these two are missing, right, okay? And then for the last digit? No. Just any, right? Okay, so what, 7? Yeah, right, okay. So there you're down to 7, okay. Great, all right. So I think that'll do it. So if you take off the restriction, right, that it's odd, just distinct, right, okay, then there's the size of S. Now let's throw back in, right? Now let's throw back in the restriction that it has to be odd. Now, when you throw in that restriction that it's odd, of course, what does that really affect there in the number?
It affects the last digit.
Yeah, it affects the last digit, right? Okay. So because that's how you tell if numbers are odd or right. Okay. So in this case, right, you may think, oh, well, it's almost the same counting problem, right? Okay. Here I have 9 choices, and then 9 choices, right, and then 8 choices, right, and then 7 choices, right, for the not 7, right, but how? Right. Okay. Maybe 5 there for the last one. Okay. But how is our reasoning here gone astray? Okay.
Because
Are there 5 odds? 1, 3, 5. Yeah. Okay. Right. Yeah.
Because you're not restricting the first 3 numbers, then they can repeat the last digit essentially.
Well, it's not that, okay, but it's almost that, all right? So you are right. The problem with describing the algorithm that way is that, we're just going to choose, again, the digits from left to right, okay? And then when I'm at the last digit, I have to make sure that I pick an odd digit, okay? The problem with that reasoning is, and this is the point that I was cautioning you about earlier, okay? this number of choices at this point, you do not know, okay? It depends on what happened earlier, right? What choices that were made earlier, correct, right? Now, why is that the case, okay? Because, see, you may have picked first here what? 1, right, okay? And, well, if you picked 2 and 4 here, that's fine, right, okay? But then how many choices do you have in the last one? 4, right, okay? Or you may have picked 2, 4, 6, which is fine. How many choices do you have there in this case?
4. 2, 4, 6, you still have 5 choices.
You still have 5 choices, right, okay? Or I may have picked 1, 3, 7, which here means I have just what? 2, right, okay? So you see that to count the executions of the algorithm using the device of just multiplying these numbers together, it has to be that these number of choices are fixed, right? It's independent of what you had chosen earlier, okay? So this is not going to work, all right? The algorithm's fine, okay? The algorithm is fine. You could execute the algorithm. I mean, you could say, okay, I'm going to pick the first one, and then I'm going to pick the second one, then I pick the third one, then in the end I got to pick so that I make sure I'm odd, right? I mean, anybody can do that, right? Okay, grade schooler could pick out such a number, correct? But, unfortunately, we cannot count the possibilities, okay? Because the number of paths of execution at the end, right, varies, okay? So, is there some way I can change the algorithm?
Yeah.
Okay, so Dotlam immediately says, yeah, what, Kaylee, what were you going to raise your hand?
So, would you do something like, I don't know.
My point is that, that's wrong, right? Okay. What?
So, for the last digit, do we just put like X such that,
Well, if you are programming the algorithm and describing the algorithm, sure, yeah, you could describe it that way, okay? And then again, it'd be easy to execute the algorithm, but the problem is so it'd be easy to program it too. The problem is I can't count the executions of the algorithm, right? Okay, that's the issue. I can't figure out how many different ways there are to execute that algorithm because of this problem. All right. So am I just stuck here, or is there something I can do different? That's right. So see, you don't have to make the choices from left to right, right? Okay. You might make the choices in a different order, okay, and that may make things easier than to count. All right. So what was your suggestion there? Start with the last number, okay? So pick the last number first, right, okay, to fill in, all right? So see, you don't, in building up this number, right, you don't have to pick the first digit and the second digit and the third digit, right? You can pick the digits in a different order, okay? So you said pick the last digit first, right? So if I do that, how many choices then do I have? 5, right, okay? So... So in my first thing I'm going to do is pick that last digit, right? Okay. So this corresponds to what? Picking what? Picking the last digit, right? Okay. Now what can I do once I pick the last digit?
Go back to picking the first digit again.
Go back, right, and now pick the first digit. Okay. So or I guess we can pick another digit, but let's go back in and pick the first digit. In that case, then, how many choices will I have, right? Okay. 8? Why is that now?
You can't include the last digit.
So you cannot include the last digit, and you cannot include what?
0.
0, right. Okay. So we have 8 choices there, correct, right? Oh, groovy. So what is this now? Picking what? Yeah, picking first digit, right? And now I guess we're home free, right? What about the next digit?
It's going to be times 8 again, and it'll be the second digit. It's 8 because it can include 0, but it cannot include 1
Yeah, that's right. So now you're down to 8, and then what's here? 7?
Yeah.
Oh, okay. All right. So, we didn't get the same number here, right? But we're not off by much, right? Okay. So this was a little bit too large, correct, right? Okay. There's the actual correct way of doing this, right? Okay. This one was what? Picking, let's go ahead just to fill that in there to make sure we recall this, right? Yeah, so this is picking, second and then third, right? So you see, again, an algorithmic approach here is really effective, but we have to think a little bit carefully about the algorithm. Just because, again, to count the executions of the algorithm, we have to make sure that we preserve the number of choices, right, at each branch point, right? That has to be a constant, okay? Cannot depend on the choices we made earlier in the algorithm. Otherwise, that doesn't mean the algorithm is not valid. It just means we can't count the executions for that, right? Ooh, we're making pretty good time here. How many integers then between 0 and 1,000 have only one digit equal to, 10,000, right? How many integers between 0 and 10,000 have only one digit equal to 5?
Somebody that only has 5 one time.
Yeah, I don't know the interpretation of that. So we're going to have to make an interpretation of that, okay? Do we want exactly one digit, or only one could mean none or one, I think, right?
If it says only 1, I think it means
Well, see, only is kind of ambiguous in English, right? So we have to make an interpretation here. Do y'all want exactly one? I think that makes it easier, doesn't it? So let's say exactly one. Okay, so all right. Now look, here you're going to mix up models a little bit, okay? All right, so when I say mix up models, it's not you're going to mix up models, but you're going to mix up methods a little bit. I think you're going to think from both a set perspective and an algorithmic perspective, okay? We'll make this problem easier, I think. But maybe I'm thinking about it too complicated, all right? So I think both of those we can put together. But I'm going to let y'all think about this, okay? The thing to keep in mind here is that when you have, is that really a thing to think about? Maybe not, okay? Maybe you can get away with... maybe you can get away with just one approach to this, okay? All right. So I'll give you all a minute there to think about it. So you've got exactly one digit equal to 5. But remember, the numbers have to be between 0 and 10,000. So it doesn't include 0, right? But that doesn't have exactly one digit equal to 5 anyway, so that's not going to be in there. It doesn't include 10,000 either because 10,000 also doesn't have a digit equal to 5. So that helps a little bit, right? Because that means you've got at most how many digits here? 4, right? Okay. Because 10,000 is automatically excluded, right? Because it doesn't have a digit equal to 5, right? So you really only have 4 digits to think about in filling in this number, okay? All right. And there's no restriction on repeated digits except for 5, okay? Which has to occur once and only once there in your number. Yeah, I think I was making it. Well, there are 2 ways to approach this, one of which is a little bit easier, but it's not quite as obvious. So just take a little while to ponder this. Wow, somebody's dongle is up here. What is that? It's a receiver for something.
It looks
keyboard receiver?
It looks like one of those wireless mouse things.
Yeah, it's either it looks like a mouse, but I think it's got a little picture of a keyboard. Maybe it's a keyboard, a wireless keyboard receiver. Okay, we don't really have to. You don't really have to completely solve the problem. I just want you to sort of think about how you would approach it, right? So that when we discuss the approach, your mind will sort of be primed to think about it.
And you said you think, do it from either way?
Yes, from either way. Yeah. Okay.
If we were using it with the models and all that, would we use something involving complements?
Maybe. Or unions.
Yeah.
I made 4 sets where one of them is integers with 1 digit.
So there's a union idea. So you're going to actually partition the big set, right, of all of these numbers, correct, into some, I hope, disjoint subsets, correct, right? So see, there is a set model that is coming into play. But I bet you're going to count those sets not with other set models, right? You're not going to count your partitions with other set models, though, I'm thinking, right? You're probably going to count those algorithmically. Is that right? Well, let's see what you described here. So you said you thought of 4 different. But what are we going to call the big set here? N.
Sure.
So there's the set of numbers, and I'm not going to rewrite those restrictions, right? All right, so there's n. So I'm going to call n sub 1 the first thing that you're going to tell me here, which is what? Yeah, so this is numbers with 1 digit, right? So see, he's thinking, oh, okay, it's got to be between 0 and 10,000. But there's lots of possibilities of numbers between 0 and 10,000 depending on the number of digits there, right, that are actually in the number. So the obvious easiest case, right, is numbers with 1 digit, right? Okay, and then you're just going to keep going here. Is this right? So you're going to count numbers with 2 digits, right? And so forth, right? So I like that. Because as I mentioned, right, there you are sort of mixing up, right? Well, we haven't mixed up yet. Let me not get ahead of you there, all right? So, but here we're using a set model, right? Because n is going to be the union, right, of these 4 sets, correct? And is this a partition? So n is the union of these 4 sets. Is this really a partition? Do these sets not overlap? Yeah, just by definition, right? They cannot overlap, right? Because we're distinguishing them, right, by the number of digits, right? So these are disjoint sets, and I think, numbers in n do have to have 1, 2, 3, or 4 digits, correct, right? Okay, so that's it, right? Indeed, we have a partition here. So if we can count these sets, right, then we're in great shape, correct, right? Because we just add up all the cardinalities, and there we've got it, okay? Now, I don't think n1 is so hard to count, correct? Okay, because we can just count that by observation, right? How many 1-digit numbers there? There's only one, right? Okay, namely 5 itself, correct? And now here's where it gets a little bit more interesting, counting n sub 2, but not much more interesting, right? Okay, so all right, so how'd you count that?
Well, in that case, you have 2 cases. Either the first digit is 5, or the second digit is 5.
So he's saying the first digit is 5 or the second digit is 5, okay? So my first choice, if I'm doing this algorithmically, would be what?
Pick a place to put a 5.
Pick the place to put 5, right, okay? So pick the place to put 5, right, okay? And so how many choices do we have there?
2.
2, right? Okay, yeah. So there's 2 possibilities for where you're going to put the 5. And then once you've done the 5, what's your second choice?
Pick fill in the other space with integers that are not 5.
Yeah, okay, right.
Do we risk double counting for 55?
Not with the way he worded it.
We don't risk it.
Not with the way he worded it.
Oh.
He said how to count the second digit, and he said don't pick 5.
Don't pick 5.
Okay.
We do have a little bit of a problem here, though, okay, with your approach, all right? So, but you're thinking that this is so let's see. So I got 2 places to put the 5, right? Okay, I got 2 places to put the 5, and then in my next choice, how many possibilities there? 9? Okay, right, because it's something other than 5, right? All right, so here's the issue here. So you're thinking this is 18, correct? All right, but the problem with that is, suppose I do the algorithm this way. I've got to pick this 2-digit number, right? So I pick 5, and I put it here. So I choose 2 first, right? Okay, I put the 5 in the second spot, and then I've got 9 possibilities. I put 0 there. Okay. Unfortunately, that gives me a
So we would have to restrict the first place more than the second place.
or do what here?
Subtract it by 1.
Subtract 1, right, okay. There's the other way, right? Just say, okay, I'm going to just exclude this possibility, correct, right? Okay, I'm just going to exclude that possibility, right? Okay, so just subtract off 1, okay, right? What you're actually doing there, so just subtract off 1 and get 17, correct, right? Okay. I'm willing to accept that. All right, logic there. What you're really doing there is you're really properly making these sets disjoint. Okay, the way you've written it, it's understood to be disjoint, right? But your algorithm, unfortunately, is producing some things in 1. So just take off those. Yeah.
It's still 18 though. He counted it right. He just didn't exclude the 5 in explaining it. But it is still 18.
Because why?
Because you have the 10 and 50, right? 0 through 9 for 50, and then you have 15, 25, 35, 45, 65, 75, 85, 95. That's 8. So 8 plus 10 is 18. So
8.
Still 18 for the size.
Okay. Wait. No. That I don't understand there, right?
The size of N2 is still 18. When he was counting it, he didn't include 5. That's what I'm trying to say.
So this is wrong here?
No, it's just like when he counted the size of N2,
Mm-hmm.
he didn't include 5. So 18 is the correct answer. So it would be 19 minus 1 to get 18.
Okay. So, but this is not 19. So what is wrong here with our algorithm? The way he described the algorithm is we choose where we're going to 5 has to occur once, right? So, and this is a 2-digit number. So first we pick where we put the 5, right? Okay, correct, right?
Oh, it doesn't include 55 in the algorithm.
Right. Yeah. Okay. So is 17 right?
Oh, yeah, but then you need to include the 55, so you could just add 1 back to it.
No, 55
Oh,
is.
right, exactly. Sorry.
Yeah, exactly.
Okay, we can only have
Okay,
one,
yeah,
so
right.
55 is 9. Sorry.
Yeah.
My bad.
All right. So we just fixed this, right? Okay. Just by saying, my algorithm goes a little bit over. Okay. So I've got to subtract off the things that the algorithm produces improperly. Not too bad in this case, right? What's going to happen in the N3 case, though? So how would you do N3?
Same thing you did for N2, but now you just add different layers.
So let's see. So I pick what? Where the 5 goes, right? 3. And then so I got 3 places to put the 5, right? Just add another slot here, right? So I've got 3 places to put the 5. I'm buying that, right? Okay. Now what?
The other 2 places can be 5, and first digit cannot be 0.
Yeah, don't worry about that yet, okay? So you put the 5 in, for instance, right? You pick that slot. Now what? Now what do you have to pick next?
Any other 2 places.
Well, don't say any other. Let's say be specific here, right? So what?
Let's pick the first.
The first remaining digit, right? Okay. So how many choices do you have there?
8.
8, right? Okay. Is it 8? No. Leave the 0 in. Okay. Yeah. Because if you had put the 5 here, see, you would be changing, right? So leave the 0 in. So how many do you have now? 9, right? And then how many here? 8, right? Okay. So that's looks like it's what? What is this number? What's 8 times 27? Or 3 times 72, however you want to think of it. 216?
Yeah, why is it 8?
Oh, I'm sorry. Yeah, we were thinking back to the earlier problem, right? So we can repeat this one. So this is also 9? Darn it. So now I have to compute again. What? 243. All right. Okay. So, but in that algorithm, right, there's 243 executions. Great. I know how many different ways I can create the digit, right? But unfortunately, I may have done what? I may have overcounted, right? So let's just take off those executions. But I think I can do that, right? Okay? Because what have we overcounted?
And what is N2?
What now?
N2, basically.
And also N1, right? Okay. Just subtract 18, right? Okay. So just subtract off of this 18, right? Because this number may have slipped in there as 005, right? And these numbers may have slipped in there, right? Okay. As 0 plus no, these numbers may have also slipped in, right? Okay, where if we had put 0 in the first slot, right, and then filled in the last 2, right? So just subtract off these, right? Okay. Well, what does it look like N4 is going to be then? Woo! All right. See how terrible this is? So 4 times what? Times 9 cubed, right? Okay. Subtracting off what?
And N2 and N1.
Yeah, that's right. So I know I'm going to subtract off 1, and I know I'm going to subtract off 17, right? And then I'm also going to subtract off, what was this one? 225. There you go. Yay! All right. So we've got our partitions counted properly using the algorithm approach, right? Now we just add up those partitions. Yeah. What now? For in which one? N2, yeah.
Why do you say that we have to pick, like I know we have to pick position for 5.
Mm-hmm.
Why didn't we just pick the first digit first, like with number 4?
Pick the first digit first because Let's think about that, right? Okay, that may work, right? Okay.
Because whenever Delta counted the number of two-digit numbers with 1 5, it counted 8. So I'm like, why do we have 7?
Well, if you do it like what you're saying, you're gonna get 9 on one and then 8 on the other one, and they add up to 17. So if you do it the way she's saying,
No,
you just do it.
because you only have 5. So you only have 1 digit, right?
You may be able to count too because it's a simple set. It's a very small set. You may be able to count that in other ways. You're going to run into trouble, though, I think, when you get to N4 because there's a much bigger set, right? Okay. So then I think this technique, the way we count it, really is helpful in that case, right? Okay. All right, so there is a set technique and an algorithmic technique, right? Okay, so that mix too. Can you think of a way that we can attack this just immediately here without?
I did it similarly. I kind of just had essentially just 4 sets. It was just like instead of separating the model out kind of like that, I just had my set was just my final answer was like 4 times 9 cubed. These and 4
That's right. Yeah.
You're
Okay.
going to be adding them all together to get n. So essentially, it's just
We really could have just used this technique, right, for counting without the subtraction. Okay, by just thinking of numbers with leading zeros, right, as being either a 1-digit or 2-digit or 3-digit numbers, correct, right? Okay, so you really could have counted the set just as N4, all right? Now remember, N4, right, though, using this algorithm could produce something like this. You might have 0, 0, 6, 5, right? Okay, but that's fine. That just in our mind would correspond to what? It does correspond to what? 65, right? Yeah, okay. So if you have leading zeros, you would just ignore them, correct, right? And that gives you the 2-digit number 65, right? Okay. So really, this is just N4 is really a direct method for creating the set. Okay. If you just think of dropping leading zeros from a number, if they end up getting produced by the algorithm, right? Y'all understand that? Okay. Because look what we were doing in 4, we were just subtracting out these possibilities, right? So just leave those possibilities in to N4 and you get the total number. So is that it? What is that? What's 4 times? Oh, we didn't count 4 times 9 cubed, right? 2,916. Cool. All right. All right. Oh, great. Darn it, we're out of time. I'll leave you all with this question. There's 2 versions of this question. So we'll take this one up next time. And then we're going to define a new set model now, okay? Because some of these problems suggest another set model that's going to be really useful to us, okay? These are called permutations. So you've heard that a term before, all right? I leave you with this question. I got 2 versions of this question, though, okay? Considerably different in difficulty. How many 5-digit integers can you construct from exactly these 5 digits? 3 1s, a 3, and an 8. So how many 5-digit numbers can you create there? Okay, that's actually pretty easy. All right. Again, think about it algorithmically, though. All right, think about it algorithmically. But this problem is. Here's a different version of that problem, all right? How many 10-digit numbers can you form from those 10 digits exactly, okay? That, if you think about that one compared to this one, you'll see what the difficulty is. And this is one where algorithms are not going to be so helpful, okay? So here we really will have to revert to a set model, all right, to answer this question. It's going to be a clever set model too, or it's not going to be direct, all right? But this one you can sort of figure out just sort of by inspection, and you can think of an algorithm to create the number. Here, much harder to think of an algorithm to, well, you can think of an algorithm, but then counting it is hard. All right, so, but can you see what the initial problem is here? You know, all ones kind of look alike, right? Okay, so you got 3 ones there. Can't distinguish one from another, all right? So that's kind of what starts lending difficulty to the problem. But it's not difficult in this version, but this one is much harder. All right, so we're going to take that up next time. All right, we're out of time. All right, so y'all can turn in your homework. Just send them over there for me. And again, I'm going to post the answers. And as soon as I've finished grading homework, I'll put I'll put a score in. So you can come by my office if you don't want to wait until Wednesday. So the test is a week delayed, right? 1 week delayed exactly. Wherever